Okay, so final page, Part D of the study team test for Chapter 10. Um, a lot of times figuring out dealing with math is difficult enough without having to try and guess what a teacher is asking because something's written unclearly. And I didn't like how this prompt was written. And I think Michael from first period helped me kind of rethink how we should say this. So let's see if this makes a little bit more sense. It says, fill in this distribution table given the following information. A study was investigating how accurate the local weather forecast was over the previous year. Rain was forecasted for 90 days. Okay, so rain was forecasted. Rain was in the forecast for 90 days. So if I look at this is the forecast, right? These rows are forecast going this direction. And rain was forecast for 90 days. So in the forecast rain, we would have it was forecasted for 90 days of rain, right? But records show that it only rained 27 days the entire year. So if, now I'm looking at, hey, this is the actual weather, right? For the entire year, it only rained 27 of the days, right? So for 27 days, it rained. You can see it was forecast for 90, but it only rained 27. Then the other thing, it says this last sentence, let's see if we can process this. It says, it only rained 7 days when no rain was forecast. Okay, it only rained 7 days when no rain was forecast. What am I talking about? I'm talking about rain with no rain in the forecast. So we're talking about this box right here, right? It only rained 7 days when there were no rain in the forecast. So there was no rain in the forecast, and yet it did rain. So there's one piece of information we need to be aware of. In a year, right, there's about 365 days. And I say about because if it was exactly that, we would never have to have a leap year or occasionally a leap second. I don't know how often that happens, but it's happened. So if I plug that in, now I understand that, hey, the forecast, we've got 90 days. It's forecast to rain 90 out of the 365 days. That means that 275 days there was no rain was forecasted, right? They have to add up. And then actual weather, rain, if it rained 27 days and there's 365 days in a year, there's not a lot of rain there. It only rained for 300 and there was no rain rather for 338 days. Other things that have to be true if these columns and rows are needing to add up. So if I look at no rain was in the forecast, but it actually rained 7. Well, this number here has to be whatever adds. It has to be the difference between 275 and 7. That's extremely clear, Mr. Roberts. Yeah, I know. This is 268. So 7 plus 268 has to equal 275. And the other thing, just these columns have to add up. So this must be the number 20. 20 plus 7 is 27. And then this number has to be 70. 70 plus 268 is 338. Now, that's all that this question asked. I could probably ask a couple probability questions like we did with the, I think, was it brown eyes, blue eyes, and green eyes, and boys and girls. I could probably ask questions like that. So I could probably say something like, I'm you know what the problem is it's late as I'm recording this, and I probably should go to bed right now. Well, let's try this out. Given that it rained, what's the percent? Given that it is a day that it rained, right? What percent of the time was the forecast correct? And let's just leave it at that. So, given that it actually rained, so this is an actual rain day, right? So, given that it rained, oh, so it actually did. So there's 27 of these days, and they're saying given that it actually rained, this is what I'm looking at. So of the days that it actually rained, there was a total of 27 actual rain days. It was only forecast to rain on 20 of those. So if I take 20 and I divide it by 27, that means that about 74% of the time the weatherman was correct, right? 74% of the time, 20 out of 27, they got it right. And if I said what was the probability that they were incorrect, that would be 7 divided by 27, and it should be about 26%, right? About 25.9%. So, okay, that's enough. Let's move on. Let's move on. Okay, so two questions here. They're both asking me to come up with an equation for exponential growth in the form y equals ab to the x power, right? So we have a zeroth term that we're starting with, that's a, and then we keep multiplying by the same value again and again and again. So if I was to try and just sketch this thing here, 0 is going through the number 20, and by the time I get to the number 3, I'm higher. So I know that this is the value of b has to be greater than 1 because this is growing, right? If I start at 20 and I make it to 67, growth is happening here. So I know that at least I know that my growth term has to be positive. Well, of course it would be positive. It has to be greater than 1. If I get a value of b that's not greater than 1, I know that I've done something wrong. The other thing that's really nice about this problem is they're giving me the value of a, right? So if I was to just take this x value and this y value and plug it into y equals ab to the x power, the y is 20 equals, and then I'd write an a times b, and my x power is 0. Well, b to the 0 power equals the number 1. So I can rewrite this as just this, right? So a is 20. So the fact that I'm given the 0th term, right, it's obvious. I know what a is. My question is now I need to figure out what my growth factor is. What value am I multiplying by repeatedly? And that's not too difficult in this case. I'm going to start with the same equation, right? Y equals ab to the x power. And this time I'm going to use this x and this y value. And I'm also going to remember that I know what a is, right? A is 20. So I've got three things I can plug in here. Y is 67.5. You can see there's the y value. It's 67.5 equals a, which is 20, times b raised to the third power. Well, I eventually want to figure out what b is, and to get a step closer to that, I'm going to isolate b to the third power, and I'm going to just do that by just showing that I'm dividing both sides by the number 20. So this is b to the third power. And I really like thinking about this as raising it to a fractional exponent. If I want to get b alone, right, this is all based on this law of exponent. If I have, for example, x to the 5th power, and I raise that to the 3rd power, then I've got 15. I have 15 factors of x, right? This is x to the 15th power. Well, same things here. If I have, for example, x to the 5th power, and I raise that to the 1/5 power, look at this magic. This is now, because I'm multiplying, that says it's power to a power law of exponents. So 5 times 1/5 is just 1. So this just becomes x. That's perfect. So what I'm going to do is I'm going to raise both sides of this equation to the 1/3 power, right? To the 1/3 power. Now, if I do that over on the left-hand side, it gives me just plain old b. And if I evaluate this expression on the right-hand side, that's going to give me what b is. So let's clear the calculator. And if I clear it, let me open some parentheses. You know what? Actually, I'm going to do it a little bit better than that. I'm going to use let me do it two ways. I'll do it with the fraction template, and I'll do it without. So I'm going to hit alpha F 1 and grab the fraction template. In my numerator, I'm going to place 67.5, and then in my denominator, I'm going to place the number 20. And then I'm going to take this and I'm going to raise it to the power of, and I'm going to use my fraction template again. I'm going to raise it to the power of 1 over 3. So that looks really great, right? And actually, I don't need the parentheses here because I left my fraction completely. This 1/3 was not in the numerator, it's in the whole fraction. I think it would be clearer to put parentheses there, but I want you to see that I get the same answer. So when I press enter, I get, oh, B is 1.5. 1.5. So another way I could enter that without that fraction key is I could just say, I'll just use parentheses. Inside here, I can take 67.5 and divide that by 20. And I can close parentheses, and then I can raise it to the power of, and then I'll put parentheses up here, 1 divided by 3, right? That's to the 1/3 power. And when I do that, I also get exactly 1.5. So we know what A is, and we know what B is. So this is just the number 1.5. So I can take my values of A and B and write my answer. My answer is Y equals 20 times 1.5 raised to the x power. Now, a nice thing to do to verify that your answer is correct is to just enter this expression, right, and then put in the number 0 and make sure you get 20. Put in the number 3 and make sure you get 67.5. In fact, if you've got time on a test and you don't do this, it's possible you're just throwing points away. So let me try this real quick. I'll just go 20 raised, nope, not raised to the power of, good grief, 20 times, I'll do parentheses 1.5, I'll just go raised to the power of. Now I'll enter 0, and you can see it says 20. That's fabulous. And I'm just going to go up, 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 grab that expression again. Going to come inside of the exponent. I'm going to modify that to the number 3. And when I press enter, you can see it says 67.5. So that took like, what, 20 seconds to plug in those values and make sure that this works. So this is the equation in the form y equals a b to the x that will go through both 0, 20 and 3, 67.5. Now there's one more question like this, and this one is just slightly more difficult, in that I do not know what my 0th term is. Now, we're going to do this two different ways. I'm going to look at a table of values, right? But I also want us to think about the equation. So here's a table of values, right? I've got some x values, some y values. I don't know the 0th term, first term, second term, third term, fourth term. So take a look at this. I'm told that the third term is 8.64. And I'm told that the first term is the number 6. So if I'm looking at this like this, this is really kind of slick. I'm going to take the number 6 and I'm going to multiply it by a b and by a b again, right? Take a look at this. And then I get 8.64. So the number 6 times a b times another b equals 8.64. In other words, 6 times b squared is 8.64. In other words, b squared is 8.64 divided by 6. In other words, b is the square root of that. If I raise both sides to the 1/2 power, that's the same thing as taking the square root, right? So I could just open my parentheses and just go 8.64 divided by 6, close parentheses, and I'm just going to now raise that to the 0.5 power, or I could take the square root. And when I do that, I get that b is 1.2. Now what's convenient about that is if b is 1.2, I now have a roadmap for figuring out how to get my 0th term. Because when as I move forward here, each time I move forward, I'm multiplying by 1.2. So if I want to go backwards one step, I'm just going to divide by 1.2. So if I take the number 6 and divide by 1.2, it should give me my 0th term, and it does. Well, I hope it does. It gave me the number 5. Now, let's write down this answer and check it. So I think the equation is y equals 5 times 1.2 raised to the x power. Now, real easy way to check it, I'm just going to type that in. So I'm going to go 5 times, open parentheses, 1.2, close parentheses, raised to the, first of all, I'm going to do the first power. This should give me the number 6, and it does. Up, up, enter, enter, and then I'm going to change that to the number 3. And when I enter 3, it should give me 8.64, and it does. So I have to say, I love multiple representations, and just the fact that changing these points into a table let me kind of clearly think about how I could write this equation, right? This 6 times b gave me 8.64. That's a great way to solve that problem. Another way we could look at it is, as a system of equations problem, kind of. I can start with this y equals ab to the x. From my first xy point, I know that y is 6 and x was a, so I can say 6 equals ab to the first. The other equation I can write is this 8.64 equals ab to the third power. So what we've been doing is solving to get a alone in these equations. And if I get a alone for this one, it's 6 over a. No. I'm dividing by b. 6 over b is a. That's one equation. And over here, if I divide by b cubed, I get 8.64 divided by b cubed is a. So if I take this expression, which equals a, and this expression, which equals a, and I set them equal to each other, that's going to allow me to solve for b. So I could just write 6 over b equals 8.64 over b to the third. So we could just go ahead and plop down b cubed on both sides. If I multiply both sides of this by b to the third, over on this side, it's just going to become 8.64. If you think about it, what am I doing? It's fraction busters, right? By multiplying both sides by b, I get rid of the denominators completely. On the other side, if I put 3 factors of b in the numerator, because I have to keep it balanced, I get b cubed over b, which just gives me 6b, whoops, not ob, so it gives me 6b to the second power. And if you take a close look, right, here's the magic. That's exactly, it's precisely what we had right here, right? These equations are exactly the same. So I was able to come to the same spot by writing a system of equations or by using a table and figuring out, what this was multiplying by. So at this point, we've already checked it. It was the solution, right? Y is equal to 5 times 1.2 raised to the x power. Okay, I'm asked to sketch a graph of a couple linear inequalities. The fact that they're linear makes them pretty straightforward to graph. This first one is y's are strictly greater than, so this is going to be a dashed boundary line. You can see that I've got a y-intercept at 1 and a slope of 1/4, so I'm going to go up 1 and then over 1, 2, 3, and 4. And I can also go down 1 and then back 1, 2, 3, and 4. Let me grab my ruler and just line those up. Once they're lined up, I'm just going to go dash, 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 dash. Now, this says y values are those things that are greater than that. So I'm assuming if I put 0, 0 in, that point would fail. And sure enough, yeah, 0 would be for y and x both. So 0 greater than 1, that's false. So I am not shading below, I'm just shading above. So this is my solution for number 4. For this one, I need to get y alone first. So I'll just write y is equal to, nope, not equal to, y is less than or equal to negative x plus 2. Again, all I did there was subtract x from both sides. No multiplication or division by a negative. So just subtracting x the inequality direction stays the same. My y-intercept there is at positive 2, and my slope this time is negative 1. So I'm just down 1 over 1, down 1 over 1, etc., down 1 over 1. So, and this one has a solid boundary line. So once I line this up, I'm going to draw the line that goes through this solid. There we go. And then finally it says, if I look at this, those y's are the things that should be below that. So I'm assuming if I take x is 0, y is 0, if I take the origin, put in 0 for x, 0 for y, this gives me 0 is less than or equal to 2. Absolutely true. So that's why I'm shading below this curve. So there is a solution to this linear inequality. And the last questions. It says, second to last, my bad. It says make a table and graph y equals 2 to the x power. So let's go ahead and pick, probably going to want a couple negative numbers there too. So let me do 0, 1, and 2, and maybe 3. But I think it would probably be wise to look at maybe negative 1 and negative 2. So if I took 2 to the 0 power, that would give me the number 2, and 2 plus 5 would be 7. 2 to the... No. That's completely wrong. 2 to the 0 power equals 1, Mr. Roberts. So when I plug in x is 0, it gives me 1. 1 plus 5 is 6. This is 6. 2 to the first is 2, and 2 plus 5 is 7. 2 squared is 4. 4 plus 5 is 9. 2 to the third is 8, and 8 plus 5 is the number 13. I think these numbers will let me go even further. Let me try the number 4. 2 to the fourth, that would be, what, 2, 4, 8, 16. And then 16 plus 5 is the number 21. The scaling is really small. Okay, so let's do a couple negative values, I guess. If I was going to go 2 to the negative 1 power, that would be a half, right? 2 to the negative first power is the same as 1 over 2 to the first power, which is just the number 1/2. And 1/2 plus 5 would be 5.5. And if I did to the negative second, that would be 2 to the negative second, which is the same as 1 over 2 to the second, which is 1/4. And 1/4 plus 5, I guess I would write as 5.25. Okay, I think I got an okay table of values here. I might want to get a couple more points, but I'm ready to plot some anyway. So at 0, I believe I'm hitting the number 6. That's convenient, it's there. So 0 goes to 6. The next point I have is at 1, I'm supposed to hit 7. It's going to be right in between the two. Okay. And then, I'm sorry, I'm zooming in and out like this. At 2, I need to be at the number 9. At 2, I'm supposed to hit the number 9. At 3, I'm supposed to hit the number 13. So 3 is going to 13. And then finally at 4, I should be hitting the number 21. So at 4, I'm at 21. And you know, these are great. These are super. Let's see. Negative 1 should be at 5.5. Negative 1 here is 5, and then halfway between this point, and so about right here. And then it should be like at 5.25. Oh, you know what? This line right here, y equals 5, is an asymptote, isn't it? So I'm approaching this line, y equals 5, and I should be very careful when I'm sketching this not to cross that line. So let me take this, a very thin green line. I'll just put it right through there, right? So everything should be, well, I don't know why I did a 1 degree line. That looks awful. It had a slope. I didn't want a slope. I wanted this to be 0. So I just have to make sure that as I sketch this, that I'm really clear that it doesn't go below that. And if you think about this, if the plus 5 wasn't there, right, what that plus 5 is doing is it's just shifting the function 2 to the x power. It's shifting it up 5 units. So normally this 2 to the x power would have a asymptote that would be the x-axis, that line y equals 0. But here it's going to be this line y equals 5. Y equals 5 is an asymptote here. So if I was to try and sketch that, I'm not a very good sketcher of functions. It's like, I'm just being careful. I don't want to cross the green line. I don't want to make it look like I'm even thinking about crossing it. I should get one more bigger value here. If I put in 5, I think I could do this. 2 to the 5th power, that's 2, 4, 8, 16, 32. And 32 plus 5 is 37. So is the 37, is there room for 37? Yeah, there is. So 37 is right here. So this function is going like, there we go. Now, of course, this is kind of, I don't know, it seems like it's, well, why would you do this now? You've already done all the work. Because you know what? It's just nice to see if you can like graph a function without the calculator. It's not that difficult. But I do want to come in and take a look at this on the calculator. So I'm going to raise 2, not 2 times x, 2 to the x power. And then I'm just going to add 5 to that. Now I notice, and I like how the 84 ROM shows this now, that I've got my plots turned on. So I can come up here to this plot, press enter, and oh wow, are you kidding right there? I just turned it off. That's so cool. Let me come over and turn this one off too. Sweet. Now those plots are not going to get anywhere near in the way. If I wanted this window to look like the graph that I'm looking at, I can see these things. That this is going from -6 to +6 on x, and from y, it's like I'll make it like negative. Oh, I want to make the y scale 1. I'll put like -1 up to the number 40. And if I graph it, it's going to look pretty much exactly like the piece of paper, except it's not a piece of paper. All right. The other thing I could do is I could hit trace, right? And I could, no, not on the function. I can hit table. That's what I wanted, table. And I could just see if I made some goofy arithmetic mistakes. But I can see 0 is going to 6, 1's going to 7, 2's going to 9, 13, 21, 37, yeah. And if I went up, I could see the negative ones. Perfect. All right, last 2 questions. We're asked to rewrite the following expressions without parentheses, right? We're performing some multiplication here. We're multiplying a binomial times a binomial, and in question 8, we're multiplying a binomial times itself. So one of the things, and although I don't think it's necessary with this problem necessarily, whatever, just be quiet. I don't think it's needed, but I do like to consider generic area models, right? If I'm doing some multiplication, it helps me avoid some errors. So I am multiplying, for example, x plus 2y. So you see there's 2 things. There's the x and then there's the 2y. And I'm multiplying that by x and a -3y. So there's 4 values that are going to comprise this product, right? One of them is x squared. Another thing that I have is this negative, let's see, what is this going to be? This is going to be -3xy. And I'm going to have a positive 2xy. And I'm also going to have a -6y getting squared. So if I look at the parts here and I write this, and I do have to combine some like terms, right? These are like terms. So my final answer is going to be x to the 2nd power minus a single x times y, right? Because if I combine -3xy plus 2xy, I just have the single xy. And then finally a -6y to the 2nd power. So that's the product for number 7. For number 8, of course, the goofy thing is, remember, you're multiplying 2x minus 1 times itself. And I know the overgeneralization and laws of exponents happen here all the time, but don't do that, please. So I'm going to sketch a generic area model just to slow myself down and help me think about this and not make that error. So I'm multiplying a 2x minus 1 times a 2x and a minus 1. So in this corner I have 4x squared. This would be negative 2x, and this is also negative 2x. And finally, negative 1 times negative 1 is just a positive 1. So my answer is 4x squared, and then I've got negative 4x. You can see there's a negative 2 and a negative 2, which combines to give me negative 2x, and then finally plus the number 1. So this is the product for number 8. Well, that's the end. That was all 4 parts of the study team test. I think I took about 30 minutes for each one of those. So hope you find these useful. You know where you can find me on campus. This is Mr. Roberts. Have a nice evening.